Let's finish off lesson 12.5 by looking at a few more examples of trig identities. So here's where we stopped with our last slide, and we have the reciprocal trig identities. Secant A equals 1 over cosine A, cosecant A equals 1 over sine A, and cotan A equals 1 over tan A. And these are simply ratios like we had with the first three trig ratios, but you'll find that each one of these ratios from the triangle are reciprocals of the originals. Expressing trig ratios in terms of sine and cosine simplifies identities. So when we're working a couple of these problems, the idea is to substitute with more familiar identities to be able to work them. In relation to, as an example, in relation to cotan A equals 1 over tan A, we can apply the quotient identity to derive the trig ratio tan x equals sine x over cosine x. So all they're saying here is when you have an inverse ratio here, you can actually express it as a similar ratio that is not a reciprocal. So from our book, we've already learned that tan x equals sine x over cosine x. Now, how do you know which is which? What they're telling you here is this 1 over tan A, or we could say 1 over tan x, is equal to the sine x over cosine x. And this can be proved by using the ratios in the triangles. But if you were to just write these down as notes, this would be something that would always be true. So my recommendations would be, whenever you see any equality in the last lesson or this lesson, that you write down that equality so it'll be there for you to use immediately. And this ratio leads to the second quotient identity. So this is the first identity for quotient identity, and this can be derived to also say cotan x equals cosine x over sine x. So look at this. This is tan, and it's sine over cosine. This is cotan, and it's cosine over sine. So if you break these things up and take a deep look at them, you'll see that they're very similar to what we've already been doing. Now, when we say sine x, we're talking about actually a whole ratio here, instead of just having maybe opposite over hypotenuse. Sine x is actually opposite over hypotenuse and over cosine, which is opposite over adjacent. So you have actually double ratios on top of each one of these. Example 3 says prove that sine x times secant x equals tan x. And this is how they prove it. The actual proof is much longer, so it's really not as understandable as it could be. So they restate that. It basically is sine x secant x equals, and instead of saying tan x, they break it down to something a little more understandable. And they should have had a first ratio here, and they didn't do it. Do you see where it says tan x equals sine x over cosine x? Well, they've taken that and broken it into two terms. You have a sine x, which normally would be in this fraction, and they've moved the term over and replaced it with 1. And the idea is so you can eventually simplify and remove this denominator. So we restate, and it was like they were working backwards. Now they show the sine x secant x equals sine x over cosine x. So we're back to what tan x actually looks like. So they broke this down into an easier equation so you could see what its component parts are. But now we have essentially the ratio that we need to prove that it is tan x, because we already learned that tan x equals sine x divided by cosine x. Very confusing. So example 4 is a proof of an identity, and because these are proofs, they are difficult. They're not just doing the problems. So it says prove that 1 plus cosine x times 1 minus cosine x equals sine 2x. And for those of you that have any memory of algebra, you'll realize something when you see these two terms being multiplied. We have a 1 plus and a 1 minus. And in algebra, when you have that, you use FOIL to multiply these binomials. And with FOIL, by multiplying them, we end up with this long expression, 1 plus cosine x minus cosine x equals cosine, and this should say cosine squared, sorry. And these two will equal each other's out, and so you actually have 1 minus cosine squared when you simplify. So this whole example is just to show you when you're multiplying two of these terms that are identical with the exception of their addition and subtraction inside, that it's the same as when we used to multiply binomials like that. You'd only, instead of a trinomial as an answer, you'd end up with one term here, or two terms, one binomial. And 1 minus cosine squared equals sine squared x. Now, this is part of the PID, and this was from the last video, which actually gave us somewhere in there it said sine 2x equals this. This is where it gets complicated because we haven't spent time doing a lot of the algebra that's required with this. So this could also be proved by subbing 1 minus cosine squared x for the sine 2x here right in the beginning. You would sub it on the right side, and you would factor the difference of two squares. So they're using this as an example. So the secant, remember that secant or sine 2x means the square of the whole term. So it's also possible to sub even when a quantity is squared. So if you have a squared quantity, and they're referring to the fact, I'll go back to this, we subbed for tan x here. What they're saying is it's possible to sub even if you have a squared term like secant squared x. It actually equals 1 over cosecant squared x, and that's because this is its reciprocal right here, and that's part of the PID. So example 5 is another proof. Prove that cotan squared x plus 1 equals cosecant squared x. And they go ahead and place both terms. Basically, the whole goal behind this is to sub something easier for the cotan 2. And I'm not sure that it's that easier. So we have cosine x over sine x, and what they've done is they've taken this 1 and they went ahead and made sine squared x over sine squared x, which equals 1, and they've done that so they can eliminate the denominator, or well, they can make 1 Remember when you're adding fractions, you had to always change one so it had the same denominator? That's exactly what they're doing here. So now you can add across, and you have cosine 2x plus sine, and you know what? This is supposed to be squared. I'm sorry about that. And let me get it to that point, because I'll do this again the next time I talk about it, and it'll be a problem. This one doesn't seem to want to superscript. We'll see what happens. Okay. All right. So now you're able to add across, and these combine on the bottom. And mysteriously, they suddenly reduce to this. Well, cosine squared x plus sine squared x equals 1, which you wouldn't remember, but here it's way back when we first started. And it's done this way by applying the PID again. And this is actually the reciprocal of this statement, cosecant squared x. And that's the definition of the cosecant ratio. So all I'm going to say about these is I'm not expecting you to be able to do them at this point. So, but understand the process of what they're doing. They have some terms that they're setting equal. All of these proofs are equalities. And they're subbing what they consider to be easier ratios so that you can actually break them apart by either factoring or by adding or by multiplying, so that you can state that a basic ratio at the end is true. And that's what they're doing. So your homework has been revised to be number 13, 15, 17, and 19. Number 13 and 15 are to prove each identity. Number 13 is exactly like example 3, and number 15 is very similar to example 3, so give that a try. Number 17 and 19 are merely working out the ratios for the new trig ratios we learned in this lesson. So instead of doing sine, cosine, and tan, we're doing cosecant, secant, and cotan. And the process is to realize what the ratio is. Cosecant 60 is hypotenuse over opposite, and that compares to your triangle. That and you have to remember which triangle has square root of 3 in it. So I would draw your 30, 60, 90 triangle and your 45, 45, 90 triangle with the numerical values for the triangles, and go ahead and solve this. And so that's how you'll do 17 and 19. And that's going to be it. We're not doing 21 and beyond, because they're all proofs. So be sure to contact me if you need any help, and we'll talk to you soon.